Now in this presentation, I'll be explaining the effect of source impedance on the performance of a single phase full wave converter. Now let us see the effect of source impedance on the performance of converter. Now this is a single phase full wave converter. And now this is a source inductance that is considered. I mean here in the absence of the source inductance, as we have already seen in the previous presentation, the transition from from the outgoing SCR to the incoming SCR, the current transition will be instantaneous. As example, that if the source has an inductance and resistance, that is, because if the source is having an inductance as well as resistance, because of the inductance, the effect is that the current through the incoming and outgoing SCR does not change instantaneously. Due to the source inductance, the current change is not instantaneous. For example, assume that there is no inductance here. If the source inductance is equal to 0, as you know that one, assume first the thyristors T3 and T4 are conducting. During the negative half cycle, T3 and T4 can be triggered. During the positive half cycle of the input, T1 and T2 can be triggered. Just for analysis, assume that during the negative half cycle, T3 and T4 are conducting. And now during positive half cycle, we are triggering the thyristors T1 and T2. Now, when T1 and T2 are triggered here, you can see that one here a reverse voltage will be coming to the outgoing SCR. Here a positive voltage comes, that gets reverse bias. Similarly, here a negative voltage comes, that gets reverse bias. So these are the outgoing SCR T3 and T4, and the incoming SCR equal to T1 and T2. And in that case, previously the current through T3 and T4 was the load current I0. And when T1 and T2 are triggered, since it is reverse biasing this one, in the absence of the source inductance, the transition of the current of this current, that is, previously the current was here I0, that's load current, and here also I0, and the current was here 0 and here 0. When suddenly this T1 and T2 are triggered here, this current is suddenly changing from 0 to the load current I0, and this current is suddenly reduces from the load current to 0, or the transition of the current is instantaneous here. In this case, if you are assuming that source inductance equal to 0. But if you consider the source inductance, the transition of this current, when, for example, if T1 and when T1 and T2 are triggered here, actually the T1 and T2 are triggered at this instant, firing angle alpha, here T1 and T2 are triggered. The current through this one, through the line that's marked as I1, the current through I1 is slowly increasing to the load current. That is, it is not transition, is not sudden. It is slowly increasing to the I0. Similarly, the outgoing SCR, that is T3 and T4 are the outgoing SCR, and the current through this one I2, that is also that is going from the load current I0 into the 0 slowly. Therefore, during this transition period, that is because of the source inductance, the transition of the current through these thyristors are taking place slowly. This is slowly dying out, and this is slowly building up. And during this period, all these thyristors T1, T2, T3, T4 all are conducting here, and the output voltage is equal to 0. That is the effect when, if you consider the source inductance or during the transition period, or that is this called the mu. This is that angle, that period we call it as angle mu here. That is for this period, that is the current transition period, that's called the overlap angle mu, and this is called the firing angle alpha. That is the effect due to the source inductance. During this period, the output voltage equal to 0. Therefore, there will be a reduction in output voltage when you consider a source inductance. And if you consider a source resistance, a resistance in series to the source here, the effect is that since the load current, same magnitude of this source current is same as the load current, we are assuming that load current is constant, therefore the magnitude is same, and because of this source current, there will be a drop in this, that is ID into RS in a single phase converter because of the source current I0. So the I0 into RS, that will be dropping here. Therefore, due to the resistance, source resistance, there will be a drop in voltage that is coming in at the input of the converter. Therefore, the effect of inductance is that there will be a overlap period during which the output voltage is 0. That angle is represented as mu, And during the because of the resistance of the source here, there will be a reduction in voltage that is at the input of the input of the converter. That is the drop in that one in a single phase case. Therefore, in a single phase converter, the corresponding equation, if you are considering there is no inductance or no resistance at the source side, the corresponding average voltage equal to 2 Vm by pi cos alpha for a single phase. But if you consider the source resistance as Rs, therefore there will be a drop in I0 into Rs. That is a drop due to the source resistance. And because of the source inductance Ls, there will be a drop in which is equal to omega Ls divided by pi into I naught. We'll be deriving this equation in the coming slides. Therefore, there will be a reduction in output voltage because of the drop in resistance, source resistance, as well as because of the source inductance. And in three phase also, we'll be seeing that we'll be deriving later in the presentation. 3 root 3 Vm by pi cos alpha is the average voltage across the converter in the absence of source inductance and source resistance. But if you consider the source resistance Rs and source inductance Ls, there will be a drop in voltage that is available. Average voltage, output voltage gets reduced in the case of a three-phase converter, which is equal to 3 root 3 Vm by pi cos alpha minus 2 I naught Rs minus 3 omega Ls divided by pi into I naught. This is for a three phase. We'll be deriving the equation in the next presentation. Anyway, if you are considering the source inductance and source resistance, because of this one, there will be a reduction in output voltage. Therefore, the Rs is the source resistance and I naught is the load current, which is we are assuming constant load current, and Ls is the source inductance. Now continuing the effect of source inductance on the performance. Now we are in this slide, we are considering that source resistance. We are neglecting the source resistance because the magnitude is very less. We are neglecting that one, and we are seeing that what is the effect of source inductance on the performance of converter. And if you are considering resistance, that voltage drop is to be considered. But in this case, we are assuming that we are only seeing what is the effect because of the source inductance. Now considering the source inductance here, in the absence of source inductance, current transfer from the outgoing SCR to the incoming SCR. As I already explained that one here, if T1 and T2 are fired here, you know that previously it was T3 and T4 are conducting. Therefore, T3 and T4 are the outgoing SCR and T1 and T2 are the incoming SCR. And so because of the source inductance, this transfer from the outgoing SCR to the incoming SCR, that transmission that is not instantaneous. That is the transfer from the outgoing SCR to the incoming SCR not instantaneously. That is shown here. That is current is slowly building up in this current I1 is and I2. That current through this leg that is slowly dying out. But during this period, all these T1, T2, T3, T4 are conducting, and we can see that output voltage equal to 0. For this angle we call overlap angle mu, and of course this is the firing angle alpha. But in the presence of source inductance, we can see that in the presence of source inductance, current transfers from the outgoing SCR to the incoming is not instantaneously. In the absence of this inductance, the instantaneous change will be there. But if you consider the source inductance, the transfer is like this. So it's not instantaneous. It takes certain time to for changing this current. Therefore, assuming load current is to be constant, if you are assuming the load current equal to constant, because a large value of inductance, we are assuming that the load current R through the RL load equal to constant. Assuming the load current is to be constant due to the large load inductance. And during the current transfer, as I already told, during this period, that is overlap period, during the current transfer from T3 to T1, T4 to T1 to T2, that is outgoing SCR to the incoming SCR. During this period, that is during this overlap angle, all these four SCRs will be conducting and the output voltage equal to 0. Therefore, during overlap angle mu, the output voltage equal to 0. Therefore, here this is the voltage that is coming at this point, and this one V2 is the voltage that is coming at this point. During the positive hour cycle, T1 and T2 can be fired. During the negative hour cycle, T3 and T4 are conducting. And here, as we are seeing here, during the transition period, all these transistors are conducting because of the source inductance, and the output voltage equal to 0. This angle equal to the overlap angle mu, and of course this angle is equal to the firing angle mu as such. Therefore, this is the output voltage. That's what that is the what that is across the RL load at this one. And of course here it is the thyristors that are conducting during the different instances are this is marked here. During this period, T3 and T4 are conducting, and during the overlap period, T1, T2, T3, T4 are conducting. Again, this period, we can see that T1 and T2 are conducting like that one. The different thyristors are conducting. Only thing is that during this overlap period, all these, for a single phase case, all the thyristors are conducting and the output voltage equal to 0. And the corresponding equivalent circuit is also shown here. This is here. During the overlap angle period or such, we can see that this is the equivalent circuit of that one. Just we are splitting. This is the voltage that is coming at this point. That is marked as here. That is minus and plus here. This is a plus point, minus and plus here. Of course, this is here minus and plus, and this is a source inductance. And corresponding current is equal to marked as I1. And these thyristors here, T1 and T2 are conducting at the same time. Therefore, T1 and T2. Therefore, this is a one parallel circuit. Second parallel circuit is that here during the negative cycle, that is this one V2 here. In that case, V2 and corresponding inductance comes here. But here during negative cycle, this will be positive and this will be negative. Therefore, here T3 comes here for LS, and then T3 comes here and T4 comes here, and here total load RL load is coming. Therefore, this is the equivalent circuit of that one. In the case of considering the source inductance LS, and we'll be deriving the equation for the output voltage across the RL load, and we'll be deriving the next slide as such. If without inductance, the equation already we know 2Vm by pi cos alpha. If you consider the inductance, there will be a reduction in voltage which is equal to omega Ls divided by pi into I0, where I0 is the load current. Omega equal to 2 pi f is the frequency, Ls is the source inductance. Therefore, there will be a reduction in voltage across the load if you consider a source inductance, and that because of the overlap period. That is this one. There will be a reduction during that period. Output voltage equal to 0. Now let us say the output voltage derivation in the case of effective source inductance on the performance of converters. Output voltage derivation. For as we have seen, this is a single phase full wave converter with a source inductance. This RL load is the load current equal to I0, and current through one we are assuming that I1, and current through equal to I2. I1 plus I2 equal to I0, and T1, this is T2, and this is T3 and T4. Of course, this is a positive group of SCR, and this is a negative group of SCRs. And when T1 and T2 are conducting, the path of the current is like this one, and when T3 and T4 are conducting, the path of the current is through this one. And here equivalent circuit of this one is for 0 to pi and pi to 2 pi, that is shown here, and this is the load that is connecting. RL load is connected at this one. And in order to derive the average voltage here, average voltage means we have to find out the average voltage this one. Therefore, here to integrate this one, that is Vm by pi. We are taking Vm, or 1 by pi. We can say that one. Now to find out the average voltage here, we are integrating this, or we are taking this area and that distributing over 0 to pi. Therefore, 1 by pi integral here, this is alpha, this is mu, alpha plus mu, and the limit, other limit is from here up to this one, it is coming, pi plus alpha is coming. Integral alpha plus mu to alpha plus pi Vm sin omega t, and that is distributed over the pi radians. Therefore, that's the average value, or Vm by pi into cos. Here actually integral sin omega t equal to minus cos omega t, and they are changing the limit. We can say that cos alpha plus mu minus cos alpha plus pi, or it is equal to Vm by pi the cos alpha plus mu. Alpha is the firing angle and mu is the overlap angle. Therefore, the average voltage equation is that Vm by pi cos alpha plus mu. And just for checking that one, as you know that if you are assuming that the mu equal to 0, that is in the absence of source inductance, the overlap angle equal to 0. In that case, if you consider the mu equal to 0 here, the equation now reduces to Vm by pi into cos alpha plus cos alpha, which is equal to 2Vm by pi cos alpha. That is already we have seen in previous presentation. That is, if there is no source inductance, the average voltage that is available equal to 2Vm by pi cos alpha. But because of the source inductance, there will be a reduction in voltage. That is, during the overlap angle, there will be 0 voltage. And in that case, the average voltage equal to Vm by pi into cos alpha plus mu, where alpha is the firing angle and mu is the overlap angle. Now continuing the effect of source inductance on the performance of converters, output voltage derivation we have derived previously, which is equal to V0 equal to, here in the previous slide as such we can see it is equal to Vm by pi which is equal to Vm by pi into cos alpha plus mu. Now here, one more, we are going to write the, or we are going to apply Kirchhoff's voltage law to this loop. We are going to apply the Kirchhoff's voltage law to this loop. In that case, we can write that this voltage is equal to V1 and this voltage is equal to V2. V2 is 180 degree shifted of V1. Therefore, we are writing that equation here, that we are going to write the Kirchhoff's voltage law equation to this loop. Therefore, here V1 is a potential rise as such, and potential drop we are taking negative, minus Ls into di1 by dt, drop across the inductance. Again here we are assuming that drop across the diode, means sorry, SCR is equal to 0, then coming back to again 0. And here, I mean, here it is the current plus to minus potential drop. That is why it is equal to minus V2. Again, it is equal to, I mean, here drop is plus minus. Here is a potential rise as a plus Ls into D, because the current is in this direction. We are considering opposite direction. Therefore, here it is equal to plus here minus here, or when you are proceeding here minus to plus, the plus sign comes, plus Ls di2 by dt, that is this current di2 by dt, that's equal to 0. Therefore, this is the Kirchhoff's voltage law equation for this KVL equation for this loop. And from this equation, we can say that Ls into di1 by dt minus di2 by dt, that's equal to V1 minus V2, or V1 equal to Vm sin omega t, and V2 is equal to minus Vm sin omega t, or V1 minus V2 equal to 2Vm by 2Vm sin omega t. Therefore, this is the Ls di1 by dt minus di2 by dt equal to V1 minus V2 equal to 2Vm sin omega t. Or one more thing is that sum of these two current during this overlap period, at any instant we can say sum of these I1 and I2, sum of this current, that is equal to constant, that's the total current I0, that is constant. Therefore, I1 plus I2 equal to I0, which is a constant. Now, if you differentiate here with respect to time, di1 by dt plus di2 by dt equal to, since it is a constant, that's equal to 0. Or di1 by dt equal to minus di2 by dt. Substituting this one in this equation, we will be getting Ls into 2 times di1 by dt equal to 2Vm sin omega t. 2Vm sin omega, 2 gets cancels. Or again, we can say that we separate the current di1, and of course here we can say di1 equal to 2 cancels, Vm sin omega t, Vm by omega L, Vm divided by Ls, Vm divided by Ls integral. We are integrating this one. The current is changing from 0 to I. The current is building up from 0 to I. Therefore, 0 to I or I0. Actually, this load current, we are assuming that I0 or I0. Therefore, here 0 to I0, the change in current di1, that is, we are from this one, from this equation, that is equal to Vm by Ls integral during that period sin omega t dt. So the change in time is equal to, actually that is changing from here during this period alpha by, in terms of time, it equal to alpha by omega plus alpha plus mu divided by omega sin omega t dt. Or in this one, substituting this here, it is equal to I0, that is I1, I0 minus 0, or I0 equal to Vm by sin omega L. Here, substituting here, we'll be getting cos alpha minus cos alpha plus mu. For I0 equal to this equation, Vm by omega L cos alpha minus cos alpha plus mu, or we'll be calculating, we'll be substituting for cos alpha here, calculating the cos alpha plus mu, and we'll be substituting in this equation. Then that is in the next slide. It is, cos alpha plus mu equal to, from this equation, cos alpha plus mu equal to, here we will get, it is equal to cos alpha minus omega Ls divided by Vm into I0. Now we are going to substitute this cos alpha plus mu in this equation, and you will be getting equation for the output voltage, and where alpha is the pairing angle and mu is the overlap angle. Again, as we have seen in the previous slide here, I0 equation is written, and we'll be getting, it is equal to cos alpha plus mu is equal to cos alpha minus omega Ls divided by Vm into Id. And also we have seen, we'll be substituting that equation, that is already Vm equal to, this is equal to Vm by pi into cos alpha plus, although this also we are derived, Vm by pi into cos alpha plus mu is the average output voltage. Now we are going to replace this cos alpha plus mu by this one, Therefore, we will be getting it is equal to cos alpha plus cos alpha minus omega ls divided by Vm into I naught. Or we will getting it is cos alpha, it is equal to 2 Vm by pi cos alpha minus omega ls divided by omega ls divided by pi into I naught. We will be substituting that for in here cos alpha plus mu here. Then omega ls divided by Vm, here Vm gets cancelled, or omega ls divided by pi into I naught. Therefore, the equation of the output voltage, average output voltage, considering the source inductance here is equal to 2 Vm by pi cos alpha minus omega ls divided by pi into I naught. Therefore, this is because of the source inductance. The drop is because of the source inductance. So if you are assuming that source inductance equals 0, the equation is equal to 2 Vm by pi cos alpha. Now, if you consider the source inductance, then there will be a drop omega ls divided by pi into id. Or this equivalent circuit, this can be written or it can be drawn as an equivalent circuit like this one. 2 Vm by pi cos alpha, that is as a source here. It's equivalent as circuit is drawn. And here, and this drop is represented as omega ls divided by pi. Omega ls divided by, and the current equal to I naught, or this output voltage will be known. This output voltage is equal to whatever this 2 Vm by pi cos alpha minus drop across this one I naught into omega ls divided by pi. That is the voltage that's mean that as the current increases, the drop here increases and the output voltage gets reduced. Therefore, that plot is plotted here. That is what is the output voltage versus the load current. What is that is this voltage V naught versus I naught. This is drawn as, this is the I naught and this is the V naught. Therefore, if I naught equal to 0, we can see that one. If I naught equal to 0, this current, this drop is 0. Or here you are getting 2 Vm by pi cos alpha. 2 Vm by pi cos alpha. I naught equals 0 and mu equal to 0 in that case. And as the load current increases, this drop increases. Therefore, so that this output voltage reduces in linear fashion. Because of this drop, the voltage is getting reduced. And at this instant, we can see that one when corresponding to, that is, this is a V0, that is when voltage equal to 0, voltage equal to 0 when this is equal to this one, that is omega ls divided by pi naught equal to 2 Vm by pi cos alpha. In that case, V naught equals 0. Therefore, this point corresponds to that one, that is V naught equal to 0, and corresponding I naught is calculated here, that is written as here. That is the current corresponding to the 0 voltage. Therefore, this is the of course it is a voltage, output voltage versus load current. Because of the source inductance, there will be a drop in voltage, and that voltage is equal to omega ls divided by pi into I naught. Therefore, output voltage equation. Now, one more equation we can derive that one. In that case, we will be deriving the equation for the output voltage equation. Here, I naught equal to Vm by pi omega into cos alpha plus mu, and here we are derived it is equal to Vm by pi cos alpha plus mu. This is the output voltage, cos alpha plus mu. In this case, we substituted for cos alpha plus, rather than substituting for cos alpha plus mu, if you substitute for cos alpha in this equation, then we will be getting another equation for the output voltage, which is equal to 2 Vm by pi cos alpha plus mu plus omega ls divided by pi into I naught. Therefore, the average output voltage equation is equal to Vm by pi into cos alpha plus mu. If you calculate cos alpha plus mu from this equation, cos alpha plus mu and cos alpha minus omega ls divided by pi into I naught, and you substitute here, then you will be getting the equation 2 Vm by pi cos alpha minus omega ls divided by pi into I naught. Now, instead of that one, if you calculate this cos alpha from this equation, and in terms of cos alpha plus mu, and if you substitute that replace that cos alpha by that equation, then corresponding equation is equal to 2 Vm by pi into cos alpha plus mu plus omega ls divided by pi into I naught. Both equations are for the same, the average output voltage V0. Now let us see a problem on the effect of source inductance on the converter performance. Like single phase full converter is supplied from a 230 volt 50 Hz source. The load resistance RL is 10 ohm and the large inductance has to be, render the load current that we are constant, making the load current constant. And if the source has an inductance of 1.5 millihenry for a firing angle of 30 degree, determine the average output voltage, angle of overlap and power factor. Now the circuit diagram is shown here. Same full wave converter, T1, T2, T3, T4. RL load is the and this is the AC source, single phase AC source, and this is the source inductance LS. Therefore, this is the topology of the circuit. And in that case, if you assume that source inductance is equal to 0, corresponding average output voltage is already you know that VDC equal to 2Vm by pi cos alpha. 2Vm by pi cos alpha is the average output voltage. Without considering the source inductance, or that voltage VDC equal to 2 into Vm equal to root 2 times its RMS value. RMS value is 230. Root 2 times 230 divided by pi into cos 30. Firing angle is given as 230. Or that's equal to 179.303 volts. Therefore, if you are not considering the source inductance, the average voltage, output average voltage across the load RL equal to 179.303 volts. Now, what is the current? Current, because average voltage you calculated V0, and the average current is given by that, because DC voltage is this one, and the average current equal to VDC divided by R. Load resistance is given as 10 ohms. Therefore, the load current I0 is equal to average voltage divided by the resistance only comes there. Inductance, the average voltage drop across the inductance equals 0. Average voltage drop, because positive and negative gets cancelled, the average voltage gets equal to 0. That average voltage here, that voltage divided by the resistance is the average, the current average, output current I0, which is equal to 179.303 divided by 10, 17.93 ampere is the I0. Now, considering the source inductance here, the corresponding equation is equal to 2Vm by pi cos alpha and minus, this is a drop across dot because of this inductance, omega Ls divided by pi into I0. I0 we calculated, and 2Vm by pi cos alpha already calculated 179.303 volts, and omega, which is equal to 2 pi f, 2 into pi into frequency is given as, this is equal to 50 hertz, 2 pi into 50, 2 pi f into Ls is given as 1.5 millihenry, that divided by pi into I0 is calculated as 17.93 amperes. Therefore, this is equal to, because of the source inductance, there will be a reduction in voltage that's equal, after reducing this drop here, we can say it is equal to 176.614 volts. Previously, it was 179.303 volt without the source inductance. Considering the source inductance, there's a drop in voltage in the inductance, and after subtracting that one, we'll be getting 176.614 volts. Continuing the problem, you are asked to find out what is the overlap angle. The corresponding current I0 equal to Vm by omega into cos alpha minus cos alpha plus mu here, which is equal to 17.93. And here, that is I0 equal to 17.93, and Vm equal to root 2 into 230 divided by 2 pi f into the inductance Ls. Actually, this is the inductance Ls, omega divided by Ls, and into cos 30 minus cos 30 plus mu. There's a mu is the unknown, overlap angle is that one. Therefore, from this equation, solving this equation, we'll be getting 30 degree plus mu equal to, which is equal to here 32.855 degrees, or that overlap angle mu can be calculated as 32.855 degree minus the alpha firing angle, which is equal to 2.855 degree. For overlap angle, that is this angle, overlap angle mu equal to 2.855 degrees, and during that period there will be output voltage equal to 0. Therefore, that is the overlap angle, 2.855 degrees. And next part of the question is that power factor is to be found out. Power factor is given by Vs into Is into cos phi is the input power. We are assuming that the switches are ideal, and the output voltage equal to V0 and output current equal to I0. V0 is the output power. V0 and VDC or IDC, or V0 into I0. VDC means average output voltage only, VDC, or that is VDC into I0 divided by Vs into Is. That's the power factor, because Vs into Is into cos phi is the input power, and this is the output power. We are assuming that there is power loss in the switches is 0. Therefore, will be cos phi equal to VDC into I0 divided by Vs into S, or VDC means average voltage, where RMS value of the source current, is same as load current. RMS value of the source current equal to I0. Therefore, cos phi equal to VDC divided by Vs, or VDC means actually it's the average output voltage, 176.614 divided by, for the RMS value of the source voltage, 230 volts, or you'll be getting 0.7679 volts. Therefore, this is the power factor At this side, this is a power factor. I mean source side power factor. Therefore, this is the overlap angle, and this is the input power factor.